Good afternoon. This is Engineering Statics. We're still using the Hibbler text. This is the 5th edition. So we're in chapter 5, and we're continuing our work through structural analysis. And we're working in trusses specifically. So we started off working through using the method of joints. Well, one of our key rules is always start with a joint. That has at least one known force and at most two unknown forces. And we can use our equations of equilibrium to solve. So we worked out several problems in our first go round with method of joints. And let's work through some more. So we turn in our text to page 238. Let's look at problem 513. Okay. This problem states to determine the force in each member of the truss as state if the members are in tension or compression. Remember, tension if it's pulling on the joint, compression if it's pushing on it. And they gave us P1 equals 10 kilonewtons and P2 equals 8 kilonewtons. So remember, if we look at the initial diagram, and if there are no joints where we have at least one known force and at most two unknown forces, then we have to start with solving the reactions support, the forces that this reaction supports. Here, let's take a look. If we start at joint D, there's one known force, P2, and two unknown forces in members DE and CD. So we can begin to work without looking at the support reactions. So let's start at joint D. So we have the P2 equals 8 kilonewton force coming down. This is FDE, the force in member DE. And we have FDC, the force in member DC. And you see how the sense of the force members, the vectors, they're arranged so that they support our equations of equilibrium, such that the sum of the forces x direction equals 0 and the sum of the forces in the y direction equals 0. FDE is positive y direction, P2 is negative y direction. FDE sense is in the negative x direction. FDE sense is in the negative x direction, FDC sense is in the positive x direction. So the forces cancel out, which is what we need. Now we need to know the angle here. They gave us in the initial diagram for the right side of the truss, and I'll draw that here. This is D, E, C. This was 1 meter, and this is 2 meters. And we know a squared plus b squared equals c squared. This would be a, this would be c. So c would be 1 squared plus 2 squared. So the square root of 1 squared plus 2 squared. Applying that to get our slope angle of member FDE, this is 1, 2, square root of 5. So focusing on joint D, if I do sum of my forces in the y direction, I have FDE times the y direction component, which is 2 over square root of 5 minus 8 kilonewtons equals 0. Solve for that. FDE 8.94 kilonewtons. Secondly, solve for sum of our forces in the x direction. You have FDC minus FDE, which we know, times the x component, which is 1 over the square root of 5, equals 0. This leaves FDC 4 kilonewtons. Now FDE is pulling on the joint, so it's in tension. FDC is pushing on it, so it's in compression. So 2 members down, let's go to the next joint. Moving on to joint C, we have FDC which we just calculated to be 4 kilonewtons. We have FCB, and we have FCE. So we have one known, FDC, 4 kilonewtons, 2 unknowns, the forces and members FCB and FCE. So if I take the sum of our forces in the y direction, you have FCE minus 0, I should say minus 0 equals 0. FCE equals 0. Let's take the sum of my forces in the x direction. You have FCB minus 4 kilonewtons equals 0. FCB equals 4 kilonewtons, and it's pushing on joint C, so it's in compression. Moving along, let's take a look at joint E. Joint E you have your FDE, which we previously determined was 8.94 kilonewtons. You have your FCE, which we said was 0, we just calculated that. You have your FEB, and you have your FEF. So we have 2 knowns, 2 unknowns we can solve. FEF, FEB are unknown. FCE and FDE are known. So if we start, let's start in the y direction. You have FE, so we need our angle once again. By the same logic we used earlier, FEB. So recreating that section of the truss, this is FEB. C, this is 2 meters, and this is 2 meters. So it's a square. So then this has to be 2 times square root of 2. Remember, for a square, each side is A, and this will be A times square root of 2, the diagonal. So that being said, we know this slope triangle, 1 square root of 2, and this diagonal we already calculated previously for this slope triangle is 1 square root of 5. So sum of forces in the y direction, we have FEB times the y component, which is 1 over the square root of 2, minus FDE, which we know, and the y component will be 2 over the square root of 5, minus FCE, which is 0, so we don't have to worry about that, equals 0. Solving for FEB. FEB is 11.3 kilonewtons. FEB is pushing on the joint, so it's in compression. Take the sum of our forces in the x direction equals 0. You have FEB, FEF, and FDE. So we have 8.94 kilonewtons times the x component. That's 1 over the square root of 5 plus FEB, which we now know to be 11.3 kilonewtons, times the x component, which is 1 over the square root of 2, minus FEF. Solving for FEF, FEF equals to 12 kilonewtons, and it's pulling on the joint, so it's in tension. Next joint, joint B. You have your P1, which is 10 kilonewtons, coming down. You have your FCB, which we calculated as 4 kilonewtons. You have your FEB, which we said was 11.3 kilonewtons. Then you have your two unknowns. You have your FBF, and you have your FBA. So FBA, you don't know. FBF, you don't know. We know FEB, we know FBC, and we know P1, which is given to us. So 3 knowns, 2 unknowns. So we start summing our forces. X direction equal to 0. You have your FBA. Oh, let me get this slope triangle back here. Same as before, 1, 1, square root of 2. So in the X direction, you have FBA minus 4 kilonewtons, which is FCB, minus your 11.3 kilonewtons times the X component, which is 1 over square root of 2, equals 0. Solve for FBA. FBA equals to 12 kilonewtons, and it's pushing on the joint, so it's in compression. Some of our forces in the Y direction. You have FBF, the last unknown at this joint, minus your 10 kilonewtons, minus your 11.3 kilonewtons times your Y component, which is 1 times square root of 2. Solve for FBF. FBF is equal to 18 kilonewtons, and it is pulling, so it's in tension. So we have 2 members left, AF and GF. So let's take a look at joint F. At joint F, we have FEF, which we calculated to be 12 kilonewtons. You have your FBF, which we determined is 18 kilonewtons. you have your FAF, and this is similar to the slope triangle on the other side of the truss. 1, 2, square root of 5. And you have your FFG. Once again, 2 knowns, 2 unknowns. So we can solve it. So take the sum of our forces in the y direction. You have your FAF times the y component, which is 2 of the square root of 5, minus your FBF, which is 18 kilonewtons, FAF is equal to 20.1 kilonewtons, and FAF is pushing on the joint, so it's in compression. Take some of our forces in the x direction. You have FEF, which is 12 kilonewtons, plus FAF, which is 20.1 kilonewtons, times the x component, which is 1 times square root of 5, minus FFG. So for FFG, you get FFG equals 21 kilonewtons and tension. Okay, so let's talk about the method of sections. So method of joints, we were using that to find the force in every member of the truss. If we only need to know the forces in a few members of a truss, you can use method of sections. And here, sections means to cut. So our technique here, you want to select a section or cut that, generally speaking, passes through no more than 3 members of the truss. And I mean in which the forces are unknown. So cut through at most 3 unknown members. So we can use our equations of equilibrium. Sum of forces x direction equals 0. Sum of forces y direction equals 0. And the sum of all your moments equals 0. So let's take a look at an example problem. Let's look at example 5.5. That's page 242 in the text. It says determine the force in members GE. Let's draw it first. A is a pin. B is a roller. You have a 1200 Newton force coming here, and a 400 Newton force coming there. And the question only wants you to find the force in members GE, GC, and BC. So GE is right here. GC is right here. BC is right here. So we can literally cut through those three members, and that will be the using our starting point of method of sections, making the right cut. Those are the three members in question, and we can cut right through them. And we don't want to cut more than three unknowns. I'm sorry. We do not want to make our cut through more than three unknown members. So at first, before we could do that, let's do our free body diagram. We said A was a pin. So this would be, you have an AY, you have an AX. D is a roller, so you just have a DY. So if we do our free body diagram on the entire truss, some forces in the X direction, you have 400 newtons minus your AX equals 0. AX equals 400 newtons. Take the sum of my moments about point A equals 0. You have your minus 1200 newtons times the perpendicular distance, which is 8 meters. It's negative because it's causing clockwise rotation about point A. You get your minus 400 newtons. Perpendicular distance is 3 meters. Plus your dy. Perpendicular distance is 12 meters. So your dy is 900 newtons. Some of your forces in the y direction. You have your AY minus your 1200 newtons plus your 900 newtons from dy. Your AY is 300 newtons. Now, so we know our unknowns from the support reactions. Now we make our cut. What side is easiest to solve? Well, if we cut here, we only have an AX and AY forces to deal with, which are 2. If we use the right side, we have 3 forces to deal with, the 1200, the 400, and 900. So let's deal with the left side of the cut because it has less forces to deal with. So let's redrawing it. If AY is, we said, 300 newtons. AX is 400 newtons. This is our G. Okay, so we made our cut, right? So then this would be our FBC. We cut through member BC, so that's the force in member BC. We have our FGC and our FGE. And this is a 3, 4, 5 triangle. The slope here. Okay. So, 3 unknowns. FGC. You have FBC, FGC, FGE. So use our equations of equilibrium. If I take the moment about point G, then we can ignore the force in members GE and GC because they go through point G, therefore they cause no rotation about point G. This will allow me to solve for members in force FBC. So that'd be FBC, the perpendicular distance being 3 meters. AY causes clockwise about point G, so it's negative. Perpendicular distance is 4 meters. And AX causes negative rotation as well. And the perpendicular distance there is 3 meters. So for FBC, it's in tension. Now, if I take the moment about point C, we can ignore FGC and FBC because their lines of action go through point C, so cause no rotation, no moment causing forces. So for about point C, this leaves only AY and GE. AX is on the same line of action as point G as point C as well. So AY causes clockwise negative. FGE causes counterclockwise positive. Perpendicular distance is 3 meters. FGE, 800 Newton in compression. Last but not least, some of our forces in the y direction. You have your AY, which is 300 newtons, minus your FGC times your 3/5 FGC, 500 newtons in tension. So that's the technique to solving these problems. Let's take a look at a problem in your text. Let's turn to page 246. Let's look at problem 517. It says determine the force in members DC, HC, HI. Okay. So we have a pin at A, and we have a roller at F. So let's do our free body diagram to get the support reactions. So I'll take the sum of my moments about point A, then the 40 kilonewton force times the perpendicular distance, 1.5 meters, plus the 30 kilonewton force times the perpendicular distance of 3 meters. The 50 kilonewton force line of action goes through point A, but there's another 40 kilonewton force with the perpendicular distance from point A of 2 meters, the line of action we're talking about. And F being a roller, so it's just an Fy there, pointing up, so that'd be clockwise rotation about point A. And the perpendicular distance here is 4 meters. Solve for Fy. Sum of my forces, X direction. You have AX minus 40 kilonewtons minus 30 kilonewtons equals 0. AX is 70 kilonewtons. So my force is in the Y direction. We calculate Fy, so that's definitely in the Y direction. That's 57.5 kilonewtons minus 40 kilonewtons minus 50 kilonewtons, and plus our AY equals 0. So AY is 32.5 kilonewtons. Now, the problem asks us to solve the force in members DC, HC, HI. So we know where to make the cut. is F, and our Fy, E, G, H, D, C, B, I, A. So solving for DC, HC, and HI, we cut through DC, HC, HI. That's where our cut is going to be. We had our AX, and our AY, we already solved. All right, so let's draw a new free body diagram, taking the cut into consideration. Okay, so got that set up. You have your force in member HI, which I'm trying to solve for. You have your force in member HC. And you have your force in your member DC. The three unknown forces where we cut through. So that we cut it, we'll do the three members in question. So now doing our method of sections work. So then if I take the moment, some of my moments, about point C, we can ignore FHC and FDC because they go through point C, which will allow us to solve for FHI. So some moments about about point C, your AX creates a counterclockwise positive, perpendicular distance being 3 meters. The AY is negative perpendicular distance is 2 meters. Minus the 40 kilonewton times the perpendicular distance of 1.5 meters. And minus your FHI, that causes clockwise negative rotation, perpendicular distance being 2 meters to point C. Set it equals 0. And solve for FHI. FHI is 42.5 kilonewtons in tension. Next, if I do my sum of the forces in the y direction, or we can take the moments about point D, whatever way is easier. If I take the sum of the moments about point D, I can eliminate FDC and FHI. And I can eliminate AY. So my AX creates positive counterclockwise rotation about point D. So that'll be 70 kilonewtons times my perpendicular distance to point D, which is 1.5 plus 1.5 plus 1.5, which is 4.5. Minus your 40 kilonewtons times the perpendicular distance, which is 3. Minus your 30 kilonewtons, which is perpendicular distance is 1.5 meters to point D. Minus your FHC, times the perpendicular distance, which is 1.5 meters. Solve for FHC. You get 100 kilonewtons in tension. Last but not least, we do sum of our forces in the y direction. You have your AY, which is 32.5 kilonewtons. Plus your FHI, which we said was 42.5 kilonewtons. Minus your last unknown member, FDC, and the slope triangle being 3/5 for our y component of FDC. Set that equal to 0. You get FDC is 125 kilonewtons in compression. Let's take a look at another problem. 525 on page 247. Here, they want you to find the force in members EF, CF, BC. So they want the force in members EF, CF, and BC. So our cut will go like here. Okay? So that cut separates the bottom half from the top half. So if we work the top half, we do not have to worry about any support reactions. So let's redraw our free body diagram after our section has been made. D, C, and E. We have the 4 kilonewton force. So here is our FEF. Here is our FCF. And here is our FBC. This is 2 meters. And this is 1.5 meters right here. So if I take the sum of the moments, about point F, then I can ignore FEF and FCF and worry about the unknown FBC. So it would be FBC times the perpendicular distance to point F, which is 1.5 meters, minus the 4 kilonewton force, so for FBC, FBC is 5.33 kilonewtons, and that is in compression. If I then do sum of my forces in the y direction equal to 0, I have my FBC, which is 5.33 kilonewtons, minus FEF equals 0. So FEF equals 5.33 kilonewtons. And that's in tension. Last but not least, sum of forces in the x direction equal to 0. I have my 4 kilonewtons minus your FCF. So your FCF is equal to 4 kilonewtons. And that's in tension. And those are the three forces: BC, EF, and CF. Take a look at another problem. 527. Here it says, determine the force in members EF, BE, and BC, and BF of the truss. So it's 4 members they wanted to find the force in. And they gave you P1, 9 kilonewtons. P2 is 12 kilonewtons. P3 is 6 kilonewtons. Okay. D is just a dy component. It's free to move in the x direction. A is a pin. Okay, so to find my forces in the support reactions, take the sum of moments about point A. You have dy times the perpendicular distance of 9 meters minus your, we said P3 is 6 kilonewtons, P1 is 9 kilonewtons, and P2 is 12 kilonewtons. So dy times 9 meters minus 12 kilonewtons times 6 meters minus 9 kilonewtons times 3 meters minus 6 kilonewtons times 3 meters. Dy is 13 kilonewtons. Okay? And they want to know the forces in EF. This is F, this is E, this is B, this is C. So EF is, it's right here, BE and BC. So if I cut here, and if I work the right side of the diagram, it'll be a little bit easier for us. So let's redraw the free body diagram using the right side. Dy, which we just calculated, as 13 kilonewtons. So you have your FBC. You have your FBE. And you have your FEF. This slope triangle here, once again, is a square, 3 meters by 3 meters. So the diagonal must be times the square root of 2. 4 squared. Diagonal is A times the square root of 2. We have our P2 coming down here of 12 kilonewtons. Let's not forget about that. It's our method of sections. We've made our section and we'll get to work. Okay. So if I take the sum of the moments about point B, I can ignore FBE and FBC and worry about FEF. So about point B, dy creates a positive rotation. And we know what dy is, so I don't have to write dy. dy is 13 kilonewtons times the perpendicular distance, which is 6 meters, minus your 12 kilonewtons times your 3 meters, minus your FEF times 3 meters equals 0. FEF is 14 kilonewtons in compression. Just point E. If I take the sum of my moments about point E, set it equals 0. I can solve for FBC. So it'll be dy, which is 13 kilonewtons, times the perpendicular distance, which is 3 meters. I don't have to worry about the 12 kilonewton force because that line of action goes through point E. FBC causes positive clockwise rotation, perpendicular distance of 3 meters. As intention. I take some of my forces in the y direction equal to 0. I have dy, which is 13 kilonewtons minus 12 kilonewtons minus FBE times the y component, which is 1 times the square root of 2 equal to 0. And FBE is equal to intention. Compression. FBE is intention. So we solve for the force in members EF, BC, and BE, but the question asks for one more. They asked for the force in members BF. All right, so then I'm going to bring in some method of joints analysis. to get the last member. So at joint B, you have FBC, which we calculated as 13 kilonewtons. You have FAB. You have the 9 kilonewton P1 coming down. You have the FBF, which is the member force in question. And you have the FBE, which we just calculated as 1.41 kilonewtons. So if I take the sum of our forces in the y direction equal to 0, that'd be FBF, the unknown member force that I desire to know, minus your 9 kilonewtons, plus your FBE, which we said is 1.41 kilonewtons. And we need to know the y component, that's the 1 square root of 2 slope triangle. 1 times square root of 2. Solve for FBF. FBF equals to 8 kilonewtons in tension. And we'll stop here for today. If there's any questions, please do not hesitate to send me an email. Good luck.